So far I haven't really said anything. Now, I want to see what kind of f's can I have that would allow my evolution to respect the rotation symmetry. You can see there are many situations where you don't have rotation symmetry. Supposing I have, in my plane, I have a little hill over here. Then it's not at all the same to be here as to be here. Here I'm close to the hill, here I'm far from the hill. This is not a situation with rotational symmetry, right? Supposing I live on a slope. I'm here, then climbing up is not the same as going down. So there are many situations that don't. But supposing we want to characterize situations in which we do have rotational symmetry, in which all the points on the plane are equivalent. And it doesn't matter if we're here, or here, or here, or here, and it doesn't matter if we have a reflection of it either. Supposing we wanted to characterize this. So we learned before that what we want is to have commutation between f and the symmetry operators. So we want kappa on f to be the same as f on kappa. What does kappa tell you? Kappa tells you, let us complex conjugate the z and the z bar. Of course, each of them. So we turn z into z bar, and we turn z bar into z. So that's kappa. And now we assemble them together into the power series. What does kappa on f do? Well, it takes a complex conjugate on f. So we're going to take the complex conjugate of this. So we have f bar, z bar m, and zn. And if these are going to be the same, well, then that tells you something. It tells you that the f, these coefficients f have to be real. So this, again, we've now restricted the form of f. Our power series has to be such that the f's are real. Now, let us write that it also commutes with s theta. So we write s theta of f, and well, what is that? Well, we know what it is. It's multiplying by e to the I theta. That's how we do rotation. And we do, so we have e to the I theta times this term. Fine. Now, let's do f on s theta. We know what s theta does. It multiplies z by e to the I theta. So we do that to z, and then we stuff it in here and do to the power m. And we do it to z over here, in here. So we have e to the I theta z, and then we take the bar and we take it to the power n. So we continue our manipulations. That'll give us e to the minus I n theta on z bar n, and this will give us e to the I m theta z bar n. And we want these two things to be the same, if f is to describe evolution which is rotationally invariant. Okay, we see these are not the same. How are they different? Well, we have z to the m, yes. We have z bar to the n, yes. But here we have a power m minus n. And here we have a power just plain 1. So we want m minus n to be equal to 1. And all the other coefficients have to be 0. So we can only have m being 1 more than n. That means we can have 1, 0, or 2, 1, or 3, 2, or all those guys. So we write all that. And we see that, just as we did before, we can pull out a z, and the whole rest of it is a function of z times z bar. So the function, we've restricted it now a lot. We've said it is any old function of z, of the modulus squared of z, any old function, that's what the f tilde is, times z. If f is of that form, then it respects the O2 symmetry. Okay, so let us write the simplest nonlinear function that respects that. Remember what we just said, we can have a constant term, and we can have times z. So we can have a z, and we can have a z times z bar. And we can have higher terms too, but let's truncate. As usual, we're going to take the smallest, the lowest order polynomial that has anything interesting in it. So we're just going to have two terms, this one and this one and this one. Okay, and let us do that. So we've written z dot equals, this is the constant term, and then this is the next term. What are the solutions to this? Well, we have solutions. I don't mean solutions, because solutions could be time dependent. What are the fixed points of this? The same process that we used in the first class. We looked for the fixed points. Well, we have one obvious fixed point, z equals 0. Here he is, z equals 0. We have another one. We have the circle with radius mu over alpha. Okay. So, can we have okay, as before, we're going to act as though mu is like a Reynolds number or a Rayleigh number. It's something that we increase gradually. Can we have a radius of mu over alpha if mu over alpha is negative? Not really. Nothing, not on the root, not in arithmetic that we know of. We cannot, so we need mu over alpha to be positive. So for mu positive, we have a circle with radius mu over alpha. For mu negative, I'm talking about alpha positive here. For mu negative, we have only this solution. When we go from one to the other, this inner point here still exists. It exists for all values of mu. You see that from this expression. But it ceases to be stable and it becomes unstable. The pitchfork bifurcation that you saw before, you could describe it this way. You start off with a point, it's in one dimension, and you're stable. And now